should be pointed out that the presence of capping agent significantly affect the internal structure of the product in addition to the surface structure. So one compelling example can be found in the synthesis of palladium nanocrystals, that is using the noble metal nanocrystals. So when a palladium to precursor was reduced by ascorbic acid in a polyol system, single crystal palladium nanocrystals were found to be dominant in the final product. So that was characterized by penta-twin structure and well-defined 100 facets on the side surface that were produced when iodide ions were introduced into the synthesis. So that was a major setback that was found by using the noble metal. So shape control synthesis, the capping agent remaining on the surface of the metal nanocrystals may compromise their performance, and that can have a various application. So when we talk about the noble metal, and it can give rise to various different shapes. So let's see one by one what are the different shapes that were found by various researchers. So when we talk about the first one, that is the cube and truncated cube. So cube is one of the most commonly observed shape for single crystals, nanocrystals, with all the 6 side faces being identical and terminated in 100 facets. So both octahedron and tetrahedron are also single crystal structures that enclosed by 111 facets. And when we talk about the rhombic dodecahedron, that is RDD, is covered by 12 congruent rhombic side faces terminated in 110 facets. So these are the various different two-dimensional structures. So as we move further, as a two-dimensional structure, a plate is characterized by a much greater area for the basal planes relative to that of the side faces. When the thickness of a plate is reduced to a several atomic layer, the two-dimensional structure, that is, we get a sheet. So that were observed with rhodium and the gold. So when we further, there are the several other singly twinned shapes for novel metal nanocrystals like bipyramid with metal like palladium, silver, platinum, gold, silver, and they gave rise to the various shapes, and those shape like beam is also were observed when we use the silver as a noble metal. In addition, there are possibly the multi-twin shapes for noble metal nanocrystals like decahedron, and then the isohedron, pentatwinned rod or wire shape, hexagonal or triangular plate, twin cube or bipyramid with metals like palladium, silver, platinum and gold. Further, we have the fanciful shapes with high index facets. So these are the highly indexed facets with other noble metal like palladium, silver, platinum, gold. So we can also have the nano powder. So nano powder, what is nano powder? So nano powder is nothing but it's having a shape of less than 1 nanometer. So nano powder refers to the ultra fine particles with dimensions measured in nanometers, offering unique properties due to their high surface area to volume ratio. And these are actually the amorphous material. These tiny particles are revolutionizing the industries from various applications, from medicines to electronics. Their ability to react quickly and efficiently makes them invaluable in various applications. So the best example of nano powder is silica, And silica, everyone knows the silica nanoparticles is transparent and its density is 2634 kilogram per meter cube. The molar mass of silica is 60 gram per mole, and the melting point, because of its very high surface area, its melting point is 1986 Kelvin, whereas the boiling point is 2500 degree Kelvin. So because of the particle size, really the silica is one of the very tough material, and that comes under the nano powder. So let's move ahead with the various properties of nanomaterial, their characteristics, how well they are synthesized, or how their characteristic properties can affect the various applications. So first of all, the characterization. So what is meant by the characterization? So characterization refers to the study of the material features such as its composition, structure, and various properties like physical, electrical, magnetic. So why we need characterization of material? Because the property of the nanomaterials varies significantly with size and shape. Accurate measurement of nanoparticle size and shape is very important, and therefore the critical to its application. And that is why we need the characterization. So we have various nanomaterials, various dimensional nanomaterials, that is one dimensional, and then two dimensional, and then we have a three dimensional material.
Basically, one-dimensional nanomaterials such as layers, multi-layers, thin films, platelets have one dimensional that extends beyond the nanoscale, allowing electron movement along their length. This unique structure endows them with distinct mechanical, electrical, and thermal properties. The two-dimensional nanomaterials are characterized by having two dimensions beyond the nanoscale. These materials, including graphene, nanofilms, and nanocoatings, are essentially ultra-thin layers where the electrons are free to move along the plane but are confined in the perpendicular direction. This results in exceptional surface area, electrical conductivity, and strength. Then we move to the three-dimensional nanoparticles. The three-dimensional nanoparticles are those in which none of the dimensions are confined to the nanoscale. This diverse class includes bulk powders, dispersions of nanoparticles, aggregates of nanowires, nanotubes, and layered structures. These materials, the unique properties of nanomaterials, are combined with bulk material behaviors, leading to wide range of applications and functionalities. So let's move to the synthesis, that is approaches of nanotechnology. So there are two general approaches for the synthesis of nanomaterials: bottom-up approaches and top-down approaches. Bottom-up approaches refers to the build-up of a material from the bottom, item by item, molecule by molecule, or cluster by cluster. This has the potential of creating less waste, and hence the more economical is the bottom up. Organometallic chemical route, reverse micelle route, sol gel synthesis,